Welcome to today's lecture. So we're still on thermodynamics. Today's lecture is very short. We're just looking at 2 units, which is just the second law of thermodynamics and the heat engines. Yeah, so I'm just going to do an introduction to heat engines, and then those that are going to do mechanical engineering, they will go deeper. Right? So here is just an introduction. We just learn how to find the efficiency and to find the heat input and the heat output. Yeah, so we'll not go into details. All right, so let's quickly begin. So like I said, we're just going to look at the second law of thermodynamics and heat engines. So refrigerators and air conditioners will be discussed in the next slide. I wanted to put them in this slide now. I thought maybe the slide was going to be long, so I left them together with entropy and the second law. Yeah, the connection between entropy and the second law of thermodynamics. Yeah, so today we're just looking at these two, so that the next slide will just summarize thermodynamics, which will just be refrigerators and air conditioners. And then apart from that, we'll also look at entropy. Okay, so what is this second law of thermodynamics? So the first law was talking about the conservation of energy, where we said the heat input or the heat gain, we said the heat gain is equal to the heat loss. This was the this was the first law of thermodynamics. Then the 0th law of thermodynamics, we remember very well, we talked about two objects being two objects being in thermal contact with the third object, which is object C. Yeah, C, and then when A and B are, when A and B are in thermal contact with the object or with another substance, which is C, this simply means that, okay, if in short, if A and C are in the same or at equilibrium, it means that A and B are also at equilibrium according to the 0th law of thermodynamics. And then the first law, we talked about the conservation of energy. And then the second law just talks about reactions in physics and in other, maybe let me just say reactions that occur spontaneously. So when you say spontaneously, meaning they are automatic, they can occur without any external force. Yeah, so yeah, for instance, when you have an object, you get this hot object, and then you combine it or you put them in thermal contact with a cold object. You know that automatically the heat energy will move from the hot object to the cold object. These are the processes that we're talking about, the processes that occur spontaneously. But the process of us having the cold moving the cold moving into the hot object, that one cannot be spontaneous. Something has to be done for that to happen. Okay, so let us see this. So the second law of thermodynamics is a statement about which process occur in nature and which do not occur. All right, so heat can flow spontaneously from a hot object to a cold object. Heat will not flow spontaneously from the cold object to the hot object. This is what I was just explaining. And then the development of a general statement of the second law of thermodynamics was based partly on the study of heat engines. Yeah, so the second law also talks about heat engines. That's the reason why I want to introduce heat engines while we're talking about the second law. So a heat engine is just any device that changes thermal energy into mechanical work. Yeah, so examples of heat engines are steam engines. Yeah, a steam engine converts the heat energy. Yeah, it converts the heat energy or thermal energy into mechanical work. we also have an automobile engine. Yeah, the engines that you usually find in cars, in motorbikes. Yeah, those engines are also heat engines. They use the same principle of heat engines. Okay, so useful heat engines, they run in a repeating cycle. Yeah, so for heat engines, remember what we said about the internal energy. We said for us is for processes that occur in a cycle which repeat themselves, normally the internal energy is equal to 0. Yeah, the internal energy for such processes is equal to 0, because you know that the work input and the work that is going to be inputted, how can I explain this? Okay, what you just need to understand is that the internal energy of all processes that occur in a cycle is equal to 0. Yeah. So the energy that will be inputted, when you add everything, the energy output and the losses, you discover that the answer will just give you the input energy. And that's what it means in other words. Okay. So that is, the system returns repeatedly to its starting point, and thus can run continuously. So most heat engines, they run in repeating cycle. Yeah, so they run continuously. They don't stop unless you just stop it manually. So yeah, that's the way it is. So in each cycle, the change in the internal energy of the system is equal to 0. This is what I was just talking about. That's heat input, which is QH. So the heat input, we're going to be calling it QH, and then the heat output, will be calling it QL. And then the temperature, the initial temperature or the input temperature will be called TH, and then the output temperature will be called TL. Yeah, so from today on, physics, those who are doing engineering should know this. This is very important for you people. Okay, so we quickly move on. All right, so here the statement says the heat input QH at high temperature TH is partly transformed into the work and partly exhausted as heat loss. Yeah, I mean heat at low temperature, at the lower temperature TL. Yeah, so what I was just talking about is, or what this statement means is that in the heat engine, there's this QH, which is just the heat input at a very high temperature, which is TH. So when you input this in a heat engine, the outputs that you are going to have, we are going to have mechanical work this side, you're going to have work output, and then apart from having the work output, you also have the TL, which is the temperature at low, I mean the what is, yeah, the temperature, the lower temperature in short. And then you have QL, which is just the what is the energy at low temperature. Yeah, at low temperature, which is QL. Right, this is what you're going to have. So when you input the heat there, then the outputs that you're going to have will be mechanical work. And then apart from work, you also have the heat losses at low temperature. Okay. So by conservation of energy, the change in internal energy is equal to the work plus QL. So the high and low temperatures, TH and TL, are called operating temperatures of the engine. So TL and TH, which is the high temperature and the low temperature, they are called operating temperatures of the engine. So note carefully that we are now using the new and initiative sign conversion for heat engines. We take QL, QH, and W as always positive. Yeah, so the direction of each engine, I mean each energy transfer, is shown by the arrow in the table below. So this is what I was just trying to draw there, where you have the QH, which is the energy at high temperature TH. Then this is the input energy there. Then the output, you are going to have QL, which is the energy at the low temperature TL. And then you also have the work there. So this can mathematically be written as work work is equal to QH minus QL. Or if you don't want to write it in this way, you can just say the addition of this work plus the QL, which is the heat loss, I mean the heat at low temperature QL, is simply just going to give you QH. Simply just going to give you QH. So you can take this QL to the other side of the equal sign, meaning you have QH minus QL. That is what you're going to have. So this is as simple as that. You need to know this. And then imagine if you want to find the efficiency of this engine. So the efficiency is simply just found by, we know that efficiency is given by the normal definition for efficiency is simply just the output. Can be how it can be output energy, it can be output temperature, it can be output anything. So it's just the output over the input. So this is just the general formula for efficiency. So for this one, we know that the efficiency of an engine, of a heat engine, is simply given by the work output, because the output, the useful work output we have is just, I mean, the useful output we have is the work. So simply just the mechanical work over the input. The input that we have is QH. So you put QH there. So this will be W over QH. So you can also simplify this. You can also simplify this. Let me just go on the next page. Okay, before I even go on the next page, let me just simplify it from here. So we can also simplify this further. While there's W, we just put QH minus QL. Say QH minus QL, and then everything divided by QH. So from there, we can divide this QH and that QH, meaning efficiency can also be written as 1 minus QL over QH. Can also be written in this format. It's very important to know that, because sometimes you might not be given the work in the question. They can just give you QL and QH. Then you have to find the work. If you want, you can find the work by subtracting them, and then you come and put them there, and then divide by QH to find the answer, to still give you the same answer. Okay. So this diagram you're seeing here, it's just an example of a heat engine. Yeah, this is a heat engine, which is in a cycle, in short. So you have a boiler here, which is boiling the water. So when the water has been boiled here by, we have the heat input here. So when the water has been boiled, it turns into steam. The steam will move through this pipe here. Then the intake valve will open. Yeah, the intake valve, it will open during expansion. So meaning the air here, as it, the steam here, as it increases, it expands. Not really expanding, but it increases, and the pressure in this cylinder increases. Hence pushing the piston. So when the piston is pushed, it will go this side. When the piston is pushed, it will go this side, which rotates the turbine. If you have a turbine here, if you are generating electricity here, it will push the turbine, and then this, and then as this turbine rotates, it will be rotating in this direction. As it is rotating, the time this road here, this connecting road is coming back this side, it will push back the piston inside. So now this will be closed. This intake valve will be closed. And since it is closed, it will lead to the opening of this valve here. So when this valve opens, it will allow the steam to go down. So as the steam goes down there, to be collected in the condenser, to be condensed, to be taken back to water, and then the water will be pumped back again. The water will be pumped back again into the boiler, where it will be boiled again into steam, and then steam there. So it continues like that. It's a cycle. That's why they say most heat engines, they run on a cycle. Yeah, there are cycles. Yeah, so to continue moving like that, hence rotating the turbine like this. The turbine will continue rotating, hence producing electricity. And then another thing that you can talk about when we talk about machines that operate in this with this principle is just the turbine itself. Yeah, so there are heat engines which have a turbine. Instead of having a piston here, the piston is replaced by a turbine which has a rotating shaft here. Yeah, it has a rotating shaft. Yeah, where if the steam is coming this side, it will be pushing it because of its pressure. The pressure will be, the pressure of the steam will be hitting these blades here, and as the blades are being forced to go down due to the pressure, this turbine, this shaft to be rotating going this side. As it is rotating the turbine which is connected to this same shaft. Yeah, so this is what happens. And as the steam comes down here, it's being released from this outlet. Yeah, so that's the principle of operation for a steam engine. So I talked about the efficiency. So the efficiency of any heat engine can be defined as the ratio of the work it does, which is W, to the heat input at the high temperature. Okay. So this is what I was just talking about. Since energy is conserved, the heat input QH must equal the work done plus the heat that flows out of the temperature, QL. Out at low temperature, sorry, QL. So this is what happens. Then from there, you can replace that there. Then afterwards, find your efficiency to be in this format. Okay, so let's take a look at this example here. An automobile engine has the efficiency of 20% and produces an average of 23,000 joules of mechanical work per second during operation. And then how much heat input is required? And then B is how much heat is discharged as waste heat from this engine per second. So here, the first question is how much heat input is required. So input heat, meaning we are looking for QH. We know that efficiency is written as work, the useful work over QH. So we can make we can make QH the subject from this formula. So QH is simply just the work over the efficiency. So the work that has been given is simply just 23,000 joules over the efficiency is 20%. When you divide that by 100, you get 0.2. So when you divide this into that, that's the answer they are looking for. That's the value for QH. So when you divide this using a calculator, since I don't have a calculator anywhere nearby, so you can divide this into that, you find your answer there. And then after finding that answer, you can use it to find the heat. The question is how much heat is discharged as waste, as waste heat from this engine per second. So if you want, you can just say work is given by, so if you want, you can say work is given by QH minus QL. Or if you don't want to do this, because you already have the useful work, you also have QH that you're going to find there. Then you just make QL the subject of the formula. If you don't want to use this formula, we know that efficiency can also be given as 1 minus QL over QH. So from there, I can just make QL the subject, which is just going to be, this will simply just be QL is equal to QH times, yeah, so when you take this to the other side of the equal sign to be 1 minus E. Yeah, so you have 1 minus E and then times QH. So you can use this, you can either use this one or this one, you still get the same answer. You just make QL the subject of the formula because they are looking for the heat that has been discharged as waste heat, which is just QL. So this is the end of our today's session. I don't know if you have any questions. I never wanted to make it long because there are also other formulas on entropies. I never wanted to confuse you with those formulas. I wanted us first to deal with the simple formulas on heat engines, so that next time, just look at the formulas that will involve entropy, and then apart from formulas that involves entropy, we also have to look at the formulas, because we know that the efficiency of the refrigerator and the the air conditioners is different from this efficiency. They are different, and for the refrigerator, you have to make sure for the refrigerator, yeah, okay, they are slightly different, but we call it, instead of calling it efficiency, we call it the COP. Yeah, and then apart from that, we also have something that is called on the refrigerators. We also, okay, before we even look at the refrigerators and the air conditioners, we will have to discuss a Carnot engine. A Carnot engine. So a Carnot engine is simply just an ideal engine. It does not exist in, yeah, it doesn't exist. They just use it. They just use it for experiments. And in most cases, as you are solving questions, you'll be assuming that all the engines that you'll be dealing with are Carnot engines, meaning and we'll come and discuss more about this. Yeah, come and discuss more as I come with the notes. All right, thank you very much for your attendance, though a lot of people came in late. Yeah, a lot of people came in late, but nevertheless, I'll send the recorded session to the group. Okay, so next time we'll come and start with the Carnot engine, and then from the Carnot engine, we'll look at refrigerators and air conditioners, and then from there, we'll proceed to to entropy. And then we'll consider that as the end of thermodynamics. All right, thank you very much. This is why I said thermodynamics is quite a long topic on its own, but the other topics will just be covering them maybe in one slide, or I mean in just one session or two sessions, we're done with one topic. This one is quite a long topic. That's why we've taken a lot of time to cover it. All right, thank you very much for your attendance. See you next time in the next session. Oh, shalom, shalom.